So 6.2, and we're now going to see what the sort of advantages of using radians are, and we begin with thinking about the length of an arc. Now I'm just going to very quickly just take you back to some, well, probably year 8 maths I should think, and we're going to talk about how you would find the length of an arc using degrees. This isn't quite how the book does it, but I use this normally. So I'm going to start by saying, well, the length L of an arc is theta, whatever the angle at the centre is, divided by 360 times the whole circumference of the circle. So that's 2 pi r. So if we're back in year 8 and we're doing arc length, that's how we do it. Now, of course, this is in degrees. We're now working with radians, and we already know that 360 degrees is 2 pi radians. So therefore I have theta over 2 pi radians times the same situation. We still have 2 pi times the radius in our circumference, but we now end up with a situation where the 2 pi's on the top and bottom of our multiplication will cancel, so we're left with r theta. So what have we actually shown here? Well, we've shown that if we are working with radians, the length of the arc on the outside, if we make an angle and the angle is given in radians, the length of the arc here on the outside can be calculated by doing whatever the radius is times the angle in the middle, and that makes life, well, fairly straightforward if we want to work out arc lengths. Of course, remember, this is when theta is in radians. Okay, that's kind of the whole point here. So if we're working with degrees, of course we continue to use our old system, but if we were in radians, it makes life much easier. Now example 3, I'm just rapidly trying to get a quick look at, because I think that's exactly what I've just showed you anyway. Let's have a look. Oh, well, have a look at their method. It's slightly different from mine. They talk about having sort of a fraction of a circle for the arc length, and then the fraction in the centre of the circle being the angle. Have a look at it, digest it, but I'm going to stick with my method for now. But I am going to move on to example 4. So let's have a look here. It says, find the length of the arc of a circle of radius 5.2 given the arc subtends an angle of 0.8 radians at the centre of the circle. I'm just going to very quickly just look at some of the terminology here. So we've got the centre of a circle, and I'm just going to try and sort of pick roughly what that might be. 0.8 radians, of course, isn't particularly big. It's maybe something approximating that. When it says, given the arc subtends an angle of 0.8 radians, that is what we're talking about. That's 0.8 radians there. And we're told that it's 5.2 centimetres in radius, and we're trying to work out this curved length here that's made. Now, we don't need to draw this diagram in reality. Of course, we know that L is r theta, provided we're working with theta being in radians. So that means we've got L equals 5.2 times the angle, which is 0.8, and it's a very straightforward calculation from that. That gives us 4.16 centimetres. Straightforward. Right, that one is done. We can move on. And it says, an arc AB of a circle with centre O and radius r centimetres subtends an angle theta radians at O. The perimeter of the sector AOB is P. Express R in terms of theta. Right, well, this seems a little bit sort of wide open to begin with. I'm not convinced we're given a huge amount here. So what we'll do is we'll draw a diagram, and then we'll sort of try and analyse it bit by bit. And I apologise immediately if... Oh, that's not too bad. I think we can live with that. So an arc AB of a circle. So here's the arc AB that I've drawn with centre O. So that's here, O, and radius r centimetres. So we'll mark the two radii in, subtends an angle of theta radians at O. So there's theta. The perimeter of the sector AOB is P. Express R in terms of theta. Well, to start with, let's come up for an expression for the perimeter. Well, before we get started with that, actually, let's just make sure we can work out what the length is. So I'll just mark that as L to start with. But what we do know is that the perimeter will equal the radius and another radius. Of course, perimeter is the distance around the whole outside of the shape. So we've got the radius, and then this length L. And we haven't worked that out yet, but we can say that that is, the length is going, actually let's go back a second. Instead of being a bit kiddie about it, let's write R plus R as 2R, and then L as R theta. So we've got the perimeter equals R theta plus 2R, or 2R plus R theta, and then that's the perimeter is equal to that. And what does the question want us to do? It says express R in terms of theta. So R in terms of theta means we need to rearrange this to get to R equals. So I think the question really should say express R in terms of theta and P. I think there's maybe just a small error on their part, but anyway. First of all, let's just take a factor of R out, so that's 2 plus theta. And now that we've factorised the right-hand side, we can now divide both sides by 2 plus theta and get P over 2 plus theta. I'm sorry about the writing, my board's at a bit of a funny angle. So we've got the radius is equal to the perimeter divided by 2 plus theta. And we're done. Example 5. Now, example 6, and we have the border of a garden pond consists of a straight edge AB of length 2.4 metres and a curved part C as shown in the diagram below that I'm going to have to draw for you. The curved part is an arc of a circle, centre O and radius 2 metres. Find the length of C. Right, well firstly let's just construct a sort of a hasty diagram. Now it's made up of a circle with a flat edge along the bottom, and actually this bottom part of the circle doesn't exist, but what does exist is we've got 2 radiuses there and there, and let's then go back through the question and make sure we put everything in. So we've got a straight edge AB, which is there, length 2.4 metres, and a curved part C as shown in the diagram. So that's this major arc around here, okay, but we're not going to pop that on there for now. And the curved part is an arc of a circle, centre O, so let's just pop that in, and a radius 2 metres, okay. Find the length of C. Well, in order to be able to work out C, we need to know the angle that we have here. Okay, that angle that goes around there. Now to work out that angle, we need to calculate this angle here. And we could do that in different ways. What's the simplest way? Well, let's just draw a triangle and look at that. So this is now OAB. There's O, there's A, there's B. We've got 2, 2 and 2.4, but I'm going to cut down the middle, so I'm going to say that's 1.2, and I'm going to find that angle using some basic trigonometry. Opposite 1.2, hypotenuse is 2. Let's call that x so that we don't get confused with theta. So we've got sine of x equals opposite 1.2 over 2, and then we can work out fairly quickly that x is 0.64643 radians. Okay, so that's for x. which if we go back to our first diagram, x of course is here. We don't want x, we need theta, which is the big angle around here, because once we've found theta, we can then use that by multiplying by the radius to find the length of the arc. So that's x. First of all, 2x will be 0.6435 times 2, which is 1.287 radians. Again, that does continue. But we then, for theta, we know that theta will equal 2 pi radians minus that 1.287 ... which allows us to work out the theta value to be 4.996. Oh, 996 radians. So that's, I'm just going to do this in a slightly different colour. That's this angle here. So I worked out what x was. I worked out firstly this, doubled it so that I got that section in the triangle, and then 2 pi radians I know is the whole way round. So if I do 2 pi minus what was green and is now blue, then that will tell me what the red section is, or what the red angle is. So I found the red angle. It's 4.996 ... Oh, I'm in blue. We don't want to be in blue. ... Radians. So in order to work out the curve length C, we do L, well, let's not call it L, let's call it C. C equals R theta, and R is 2, theta is 4.996. So we're left with 9.99 meters. And we found the curve length. And just having a look, I think that's it. Yeah, that's it for the examples before 6b. So have a look at 6b, work your way through. I warn you in advance, number 10, I think, is a bit of a stinker. So if you're struggling with number 10, do let me know. In fact, I'm certain we'll go through it as a class. I may even end up putting a video up about it on here just to save time. But in the first instance, work through the next section and give me a shout if you've got any problems. Good luck.